Okay, section 1, page 23. We're going to do a little bit of a basic electrical overview, so this will be helpful for a lot of you. There's not a whole lot of info on this page, but we can make it a whole lot of info. So starting with voltage testing, number one thing you need to remember when you're doing voltage testing is the circuit has to be loaded. Of course, we want to make sure we have a good ground. I have that listed as number 2 here. Make sure that you have a good ground, and we'll talk about that too. But a loaded circuit is what most people in this field get wrong. They don't understand voltage, and using a digital voltmeter, which is really, the most accurate way to check a circuit as far as test light voltmeter. The voltmeter is more accurate. However, the voltmeter can get you in trouble if you don't understand this loaded circuit discussion. And simply loaded circuit just means there has to be current flow. If there's no current flow in that circuit and you do a voltage measurement, you can and will get inaccurate readings. So I have an example on figure 14. This is page 25. Just a generic circuit. This was actually a live car that I looked at. This vehicle was brought in the shop, and it was a no crank situation. It would just click. You can hear the solenoid. Pretty typical for mechanics to go out with a hammer in this situation. When you hear a starter that's not cranking, it just clicks, and you smack on it a couple times. Gently, I might add. Some of these newer starters have permanent magnet field. The field magnets are permanent magnets, and you can break them, crack them by smacking on it. So it's not the greatest idea, but we've all done it. We've all bailed out a lot of people, stuck in a parking lot by smacking on the starter. So, that's the first thing you do. And of course, that doesn't work. So you get your buddies to help you push the car inside. And I start doing my voltage checks on the car. And in the first picture, what I did is I'm looking at this wire right here first. And my connections I'm not really showing, but when you're using a voltmeter, you're always, not always, but for the most part, we are looking at connecting that to a known good ground. It's important that you know your ground is good. We'll leave that part out of it for right now as far as verifying ground integrity for your voltmeter. But let's say we have a good ground, and I'm checking that wire. And one of the things about that heavy gauge wire to a starter is it's hot all the time. It goes directly to the battery. So you might not be thinking about checking that wire in a cranking situation because it's already hot. Okay? So that would be the first test, is when I check that, I have 12 volts on that heavy gauge wire. Now the purple wire that I'm showing was 0 volts. Of course, this one's going to be 0 without cranking it, because that's your solenoid control wire that comes from the ignition switch. So then the next thing you might do is you crank the engine over and you see your 12 volts on that wire. And so in your opinion, you need a starter. And the reason why is you have a good 12 volt feed up here when you checked it, and you didn't feel the need to crank it, again, on that heavy gauge wire because it's hot all the time. And you came down here and did the second test. So in your mind, you have the 2 power feeds that you need for this starter to run. And we'll leave the ground out of this equation for right now because I'm just teaching you a concept here with voltage drops. So let's just say the starter ground is good. The starter grounds on the housing of the block. The housing of the starter is the ground. It grounds to the block. Let's leave that out of the equation. Can you guys understand why we would put a starter in this application so far? We've got a good power feed, the main cable, and we got a good control wire. You throw a starter in it, it does the same thing. It doesn't crank. It just clicks. So you redo your checks, and now this time you decided to check the feed wire with it cranking, which notice now on the feed wire we have 1 volt, where before we had 12 volts. This is the loaded circuit I'm talking about. When you crank an engine over, you are loading that heavy gauge red wire in my picture, right? Loading it being there's current flow now. There's now a completed circuit. So notice what happened to the voltage. It was 12 volts with the car not being cranked, which would indicate to you that that's a good wire, but that's not a good test. because there's no current flow. As soon as there's current flow in this, that drops to 1 volt. So how do we justify this? What happens? Where did that voltage go? Well, there's a corroded cable. That's the problem. There's resistance in this cable. Would you agree with that? That if you see 12 and then you crank it, it drops to 1, that you have resistance. Now, it could be that the battery itself dropped to 1 volt and you had a weak battery. So you would want to verify battery voltage in this case too. During cranking, make sure you have good battery voltage. But you really didn't need to do that. Why? Because during cranking, this wire had 12. So it can't be a bad battery. You had 12 on the control wire, but you got 1 on the feed wire. What do you got? You got a cable problem. All right, so if that's the case and we have a cable issue, then we should, cable issue being high resistance, we should be able to do a resistance check on this cable and find it with an ohm meter, right? All right, you can't. This is the limitations of the ohm meter. You disconnect this cable, which I've done in the bottom picture, and by disconnecting the cable, I'm saying both ends need to be isolated when you're using an ohm meter. The ohm meter is the battery in the circuit. It provides a small voltage and current, looks for a return path. That's how the ohm meter works. We'll talk more about that in a minute. The point is, look at my picture. It's showing 0 ohms of resistance on a corroded cable. So how do we put all this together? What is happening here? This is probably a weak analogy, but I'm going to use it anyway. I think it gives you a good visual, okay? And to describe this middle picture and what's happening here compared to what's happening here, circuit loaded, circuit unloaded, I'm going to compare it to a garden hose, and we'll put a kink in this garden hose. Look, I even made the hose green. I'm not an artist, so I can't draw a nozzle very well. We'll just draw a little valve like that. How's that? And then the inside of the hose, we'll put some water pressure in there. And as long as the nozzle is closed on the other end, this kink in the hose would allow still pressure through, and it's going to fill this side up too. Does that make sense? That right now, both sides of this hose have the same pressure. And our pressure in this case, pressure is voltage. We'll call this 12 volts here, and we'll call this 12 volts here. In our case, you put this picture over here, this is where we're at. On this side, we have 12 volts, and on this side, we have 12 volts. Right? That corrosion being the kink in the hose. All right. So you understand that we're not going to see the issue as long as that's not a completely open circuit. We're not going to see the issue here with this corroded wire because pressure is going to fill the other side anyway because there's no current flow. Does that make sense? As soon as you open this nozzle, this would be the equivalent of flow, current flow. When we open this nozzle up, what's going to happen to all the pressure that's in this part of the garden hose? Really? Oh. Is this just going to trickle out? Where'd the pressure go on this side? It's gone. So we're down at 1 volt. Does that make sense? That's kind of putting a visual to it. It's probably a weak analogy, but it gives you an idea of why we could see the pressure loss with current flow and why we couldn't with no current flow. All right. You can think of the water in the hose as, or the pressure of the water in the hose as your voltage. The flow of the water leaving the hose would be your amperage. You need to have current flow to have accurate voltage measurements, as shown in this case study. This is exactly what happened. Now let's plug this in with the ohm meter now. Why did the ohm meter not show us this resistance? Well, what you need to understand about these positive cables is there's hundreds of strands of copper wire that are all wound together, right? We allow flexibility, hundreds of strands of copper wire. And what corrosion can do is it can break every single strand but one.
Makes them grow back like that.
It's the smartboard program in this PowerPoint. They don't get along. All right, so we got just the inside. I'm showing the inside of that cable, and every strand is broken but one. Let's talk about the ohmmeter for a second before I plug in the test. How does the ohmmeter function? An ohmmeter is the source in a circuit. You've probably learned that when you do ohm testing, there can't be voltage on a circuit. It has to be dead. And the reason it has to be a dead circuit is if there was voltage in the circuit already, that means there's pressure in that circuit. And what the ohmmeter does is it actually sends out a small voltage and current in the circuit that it's trying to test. So this ohmmeter literally sends out a very small trickle of current, and it looks for the voltage drop on the return side. That's how it measures resistance. I've actually had my students as an exercise and take a voltmeter and measure their ohmmeter's voltage. An ohmmeter actually puts out a small voltage. And on average, you'll see on a regular ohm scale, you'll see like 200 millivolts that you'll see on an ohmmeter. 200 millivolts. Now think about that for a second. The ohmmeter puts out 200 millivolts of pressure, right? With an amperage that you can't even measure. Try to measure the amperage of an ohmmeter, and it's like in the microamps, okay? So that's what we're using to check resistance in a circuit, microamps. Put the ohmmeter on a high amperage circuit, like this one. So you put your ohmmeter lead here, put your ohmmeter lead here. What does the ohmmeter do? It sends out its small voltage and current, and it finds a path without any resistance right through that one strand of copper wire, and it reads 0 ohms of resistance on that wire. So, is an ohmmeter a good tool for finding resistance problems in high amperage circuits? No, it's not. Take that thing and chuck it in the garbage can, because the ohmmeter is useless on high amperage circuits. Now, what do we define as high amperage circuits? To me, anything more than an amp of current flow, that's right, 1 amp of current flow. Anything that carries more than 1 amp of current flow, that ohmmeter is garbage. So now, why does the engineers and why do the manufacturers always give us resistance checks? Well, I don't know. I guess they think we're not smart enough to handle voltage drops. You know how many times I've done ignition coils where the only test an engineer gives you is a resistance, and they'll tell you to measure the primary, measure secondary. You know, primary should be 1 to 2 ohms, and secondary should be 6 to 10,000 ohms. And you do an ohm check on that coil, and it ohms perfectly fine, but it's a dead coil. Why is that? Because current and amperage that normally travels through those windings stresses the windings, heats them up, and it will either open or short, but it only happens under a loaded situation. So what's the ohmmeter do? It misses it. I'm not saying the ohmmeter is useless. The ohmmeter is a great tool on low voltage computer circuits because they don't carry any current flow. So the ohmmeter is very accurate on those. And I can give you another scenario where the ohmmeter is the one you want to use. And I'm going to do that here in a minute. But does this make sense on this page on why we want to do voltage drop testing, which is simply a loaded circuit? All right, I want to add another thing to this because there's a lot of confusion in this field as far as what's a voltage drop test. Well, let's do a voltage measurement or let's do a voltage drop test, right? Which one's which? What's the point? Okay, first of all, you understand right here that that is a loaded circuit, that 1 volt that we're reading on that picture, right? We're cranking the engine, that's a loaded circuit. What is the voltage drop on that wire right now as we're doing this test? Can you give me a number? So the answer was 11 volts, and that's a good answer because you're saying that the battery is 12 volts and we're at 1 volt over here. And so what you had to do in your mind before you gave me that answer is you subtracted the 2 and you told me that the voltage drop was 11 volts. That's not the correct way to do a voltage drop, and here's why. During this test, what are we doing? we're cranking the engine over. When you checked your battery voltage, what were you doing? Were you cranking the engine over, or did you just check your battery voltage? Probably you just checked your battery voltage. You didn't check the battery voltage during cranking. Is it safe to say that battery voltage may drop during a crank? And so if battery voltage dropped to 11 volts during a crank, and you read 1 volt over here, and you have 11 volts at the battery, what is your voltage drop? It's 10 volts. Does that make sense? So you're thinking correctly, but you have to account, here's the point, when you do voltage drop tests, you have to account for system voltage changes to know what your voltage is at your testing point. So it took you, listen carefully, it took you 2 measurements, 11 volts at the battery cranking, and then 1 volt at the starter cranking, 2 different measurements to determine the voltage drop in that circuit, which we now say accurately would be 10 volts. All right. Understand this, that a voltage drop test eliminates the need for 2 measurements. A voltage drop test, which I'm not showing in this picture, would be like this. If you wanted the voltage drop on this heavy cable, what you would do is you would connect your voltmeter, 1 lead to the post and the other lead to the other end of the wire. It's a positive to positive test. And it's confusing because if you think about it, if you're reading 12 volts over here and 12 volts over here, which you would be up in this test up here, 12 at each end, well, I made that an ohmmeter, voltmeter, 12 and 12. What does the voltmeter read in that case? What's the reading on the voltmeter? If both ends are connected to 12 volts. This is another characteristic of a voltmeter that you need to understand. A voltmeter reads difference in potential. It doesn't read voltage. It reads difference in the voltage between the 2 leads. Okay? So a voltmeter reads difference in potential. What is the difference in potential between my 2 leads right now? 0. So what does my voltmeter read in this top measurement up here? It reads 0 volts. So you can see how that can be confusing, can't it? Right? You're expecting to see 12 volts on a circuit, you're doing a voltage drop test, and you're reading 0 volts. But you have to shift your mind a little bit because in this test, 0 volts is good. 0 volts is good. 0 volts means between battery positive and starter BAT post, there is no difference in potential, which means that wire is good all the way end to end. Now, we still have an issue. We're not cranking the engine over. So it's still not a good test. What do you have to make sure you're doing when you do this voltage drop test? You need to make sure you're cranking the engine, and if we crank the engine, this side drops 1 volt, right? This side's at 12. Well, let's say that while we cranked it, it dropped to 11. What's the voltmeter going to read? It's going to read 10 volts. So do you see that a voltage drop test is really the same thing? It's just we didn't have to do the math. It did it for us. But it can be confusing because doesn't 10 volts look better than 0 volts in our mind? When we do voltage measurements, doesn't 10 volts sound better than 0 volts? It's not on a voltage drop test. So voltage drop is power to power, ground to ground. And the reason we do those tests is we don't have to do 2 measurements. Okay? So that's a voltage drop test. But in both cases, you have to have the circuit loaded. Now, I don't commonly do power to power voltage drop tests because we can safely assume in most applications that we have 12 volts at the battery when we're doing our checks. If the engine's running, of course, we're going to have 14 volts. So those are things you need to think about. You know, you might do a test, say, on an electric fuel pump that you're only reading 9 volts back at the pump. And you're like, wow, that's pretty low. But you have to think about the state the car is in. If you're back there checking the pump, the car probably doesn't run, and you're cranking the engine over, and you've probably been cranking the engine over for a while trying to find a good ground under that rusty frame. And so what have you done in the process? You've lowered the battery voltage and you're cranking it. So, cranking voltage at 9 would be bad, but the point is, the reason you're so low back there at the tank is your system voltage is low. So when you're not doing voltage drop tests, you always have to have in mind, what is my system voltage during this test? Voltage drop. You have to have a loaded circuit. All right, let's expand on that for a second with our voltmeter. And my next one that I'm saying is you have to have a good ground. You have to have a good ground. And this is something I see my students do on a regular basis, is they don't understand how important it is to check your ground connection before doing any measurement. Now, you guys were probably taught, check your meter, right? Was it stressed to you guys that you need to check your meter before you use it? In all applications, check your meter, check your meter, check your meter. And so what you end up seeing people do when they're, quote, checking their meter is they'll grab the meter and they're at the battery. So there's positive and negative. We're going to test something way over here. But you're going to take your voltmeter and you're going to connect it like this to the battery and you read 12 volts. So you're like, cool, I just checked my meter, right? And then you take your meter away from the battery and then you come over here, you connect your meter to some piece of metal and you connect to the positive wire. And this test that you did over here is a complete waste of time. Because when you check your meter, what you are doing is you're checking your ground connection. That's what's important. Now think about this for a second. You got a component that isn't working. And let's pick on a fuel pump again. I just shot a video on it. Actually, I'm uploading it right now. I'm using a test light, but it's the same kind of thing. If you're checking a circuit for a power feed, and there's no power there, you're going to turn left. If there is power there, you're going to turn right. So just think about it. You're traveling down a road and you have a map and like, no power, we're turning left. We got power, we're turning right. Okay, so let's say we don't have power on our circuit that we're checking. So we turned left. But the problem was your ground connection was bad for your meter, so you didn't read the power that was there. Guess what you're doing now? You're going the wrong direction. So how important is it when you measure a circuit and you read, say, 0 volts on a circuit, that you are 100% confident that your ground connection's good on your meter? How can we be 100% confident that our ground connection is good? Here is how. Don't waste your time over here unless you can leave your negative lead attached to the battery when you're done. Because when you check your meter and you're connected to the battery and you touch battery positive, one lead attached to battery negative, one lead attached to battery positive. If you can leave battery negative where it is, are we good to go now? Are we confident that when I touch my positive lead on something else, whatever reading I get is going to be accurate? We are. If you can't stay at the battery because the component you're checking is too far away, I'm connected to what I think is a known good ground, what do I do before I connect to this component on this side? Find a known good power feed and use it to check your ground. I'm not worried about my voltmeter. In all the years I've been doing this, my voltmeter's always worked. What is always an issue? The ground connection for my voltmeter. So if I'm inside the car and I'm checking, say, a brake switch for power, what can I use inside the car that would be a known good power feed? Feedback. What would be a known good power feed inside the car that I can use?
Cigarette lighter.
Cigarette lighter would be okay. Be careful with your lead. Don't go crooked in it. You'll blow the fuse. What else? Yeah, maybe dome light. If the dome light's on, pop the cover off. Put your lead right there. Pin 16 of the data link connector. It's hot all the time. I use pin 16 not necessarily to check pin 16. I use pin 16 more to verify a voltmeter ground connection when I'm inside the car more than I do anything else. What about fuse box? Fuse box might be right there. Turn the key on. Check one of the fuses for power. What are you doing when you do that measurement? You're checking your ground so you can rely on your reading. And so just to wrap that part up, I want to say this. Every single 0-volt reading you get on a voltmeter, what is your next thought before you start attacking that circuit as if it has no voltage? Your next thought must be, is my ground good? And even through a diagnostic process, even though I've checked my ground before and made sure it was good, what am I doing again before I make this call or before I continue or turn left in my example? What am I going to do? Double check your ground. How important is that? Seems so fundamental, so basic, but do you know how many people miss that? It's amazing how much people are willing to start chasing some kind of problem, and the problem is your voltmeter doesn't have a good ground. All right, so why do we want to use battery ground when possible? I've seen a few cars that actually have a bad block ground. I have a video on this showing it, a bad block ground. So if we're using something else metal in the car and none of that has a ground, you're going to get inaccurate readings. So we want to use battery negative whenever we can, when possible. 4 or 5 times I've seen broken grounds. They'll throw you for a loop, for sure. Okay. Now before we go into the average reading part, let's talk about a ground to ground voltage drop test, because this is something that I use frequently when I'm doing sensor circuit diagnosis. You'll see in a lot of my videos, I'm checking sensor ground with the key on, and I'm giving you a number of 100 millivolts or less. So let me just put a simple sensor circuit up and talk about what a bad ground would look like. I'm just going to throw up a coolant sensor circuit. And what a coolant sensor circuit will do is, it's basically a simple series circuit, 2 resistors. There's an external resistor out here. There's an internal resistor inside. Computer will send 5 volts across this first resistor, and it has to travel through another resistor before it gets to ground. And, you know, we'll do more of this later, but one of the things that you'll learn about voltage drops is there has to be current flow to take place for a voltage drop to take place. And that goes with our analogy with our, corroded battery cable. When you check this circuit, now this would be the signal wire. This is your ground wire, and we're going to focus on the ground. When I connect and check a sensor ground, the key is on. Why does the key have to be on? Because I need this source to be here. If the key is off, there's no 5 volts there. As soon as I turn the key on, is my coolant sensor circuit loaded? Yes, it is. And I don't want to unplug the sensor when I check this, and I'll show you why. But what I do is I'll T-pin the ground wire, connect my voltmeter to a known good ground, hopefully battery ground, and I want to see a reading here of less than 100 millivolts. Now, what would a corroded ground look like? Watch. Think about pressure, think about a garden hose. If I put some resistance in here, think of that as another kink in the hose. What's the pressure going to do in this leg of the circuit if there is a restriction right here? Is this going to fall, or is this going to rise in pressure? If you visualize the hose, that's right, it's going to rise in pressure. So will I see maybe 1.2 volts? Would that be a good ground? No, it wouldn't. It's kind of weird that we're talking about a ground to ground voltage drop test, but how accurate is it? It's extremely accurate. What would this circuit look like if this ground wire was completely open? What would I see on that measurement right there? What would the voltage be? It'd be 5. It would read 5 volts right there. I have 5 volts going across one resistor on its way through to another resistor. However, there is no current flow, so there is no voltage drop. So an open in the ground would read 5 volts on that wire. This is a basic electrical fundamental that you just need to accept. It doesn't matter if I send voltage through put a switch here. It doesn't matter. I'm sending 12 volts through 4 different resistors. If I take a measurement right here, I'm going to read 12 volts all the way at the end of that circuit, as long as that switch is open. There is continuity through. It's not an open circuit. So with no current flow, that pressure finds a way, just like water does. And what's it do? Fills up every section of that hose with equal pressure. Doesn't matter if there's 1 kink or 4 kinks in the hose. Does that make sense? It's a fundamental that you just need to accept. No current flow, no voltage drop. What's that? It doesn't? Which part?
No, I mean, I get it.
You get it?
Yeah, as you just, it doesn't seem like there should be 5 volts there if there's no place for it to go.
Yeah, well, that's just it. There is no place for it to go, and so the pressure stays the same because there's no current flow. You're putting pressure through this leg of the circuit, and you're going to read 5 all the way out here, even though there's resistance. And I know you're always thinking resistance, is going to cause a voltage drop, but resistance doesn't cause a voltage drop if there's no current flow. It won't. Have to have current flow. So can we pick up ground problems by simply doing ground to ground voltage drop tests? Yes, but what's the key?
That's a good ground.
Well, I gotta have a good ground on my meter for sure. More importantly, what's the key with this circuit measurement is the key's gotta be on. Here's why, watch. If I shut the key off, this is gonna be 0 volts here because the computer doesn't send the 5 volts out. So what does my voltmeter read? My voltmeter reads 0 volts. So on a ground to ground voltage drop test, reading 0 volts would be a good number. So what I'm showing you is with the circuit off, 0 volts, you think you have a good ground, but you don't. You have an unloaded circuit. Does that make sense?
Have you ever
Circuit has to be loaded.
Have you ever seen an engine ground, like someone goes to turn the key and it sparks? Right?
Yes.
What is that?
Question was, have I ever seen an engine ground when it's cranking spark? That would be a bad block ground would cause that. A bad block ground would cause that. Let's back this up for 1 second. There's one thing I missed. I'm sorry. I want to address this. Why does voltage drop? So let's say we're 12 here on this side of the corrosion, and we're 1 volt here. Now, I know I explained the garden hose analogy, but why is it actually dropping? What's causing the drop? The answer is heat causes the drop. Copper wire acts as a positive temperature coefficient resistor. Big word, PTC resistor. What a PTC resistor is as, here's your PTCs, positive temperature coefficient. As temperature goes up, resistance is going to go up. What's an NTC? Which is all of our thermistors. We'll be doing this more later. Temperature rises, resistance falls. The way I always remembered an NTC is they're always opposite of each other, right? PTCs, they go up together. Copper wire is a positive temperature coefficient. So if I have 1 strand of wire left, maybe a couple strands, that it takes 1,000 strands to carry the 200 amps of current the starter needs. What happens if you only got 3 or 4 left? Major heat. So what happens with major heat? In that section of wire right here, what happens in here? What happens to the resistance? Resistance goes super high, which happens, and so if resistance goes very high right here, what happens to voltage as it travels across it? It drops. That's why that's happening. It's heat that causes it. Did you know that more times than not, when you have a wire that's burnt up, it is from resistance causing heat, not from too much current flow. Do you know how many times I've seen a connector burnt up and the person that sees that, technician that sees it, says, oh, maybe it's to a cooling fan. And they say, oh, that's a bad fan motor. The fan motor drew too much amperage and burned up the connector. That's not the right answer. That's not what happened. Corrosion set in first as a green cruddy connection. And so what does that green cruddy connection do? It makes resistance. And what does resistance make? It makes heat. And what does heat do in the wrong place? In a location where heat shouldn't be. It melts the connector. And so the burned up wire and burnt up connector is not from too much current flow. It's from a resistance problem that created heat. That's what happens. All right, let me finish up the voltmeter thing and we'll take a break. Right here, last statement. Voltmeter reads difference in potential. This is important to understand, and it has to do, again, I told you guys, voltage drop testing. A voltmeter reads difference in potential. If my voltmeter positive lead is connected to a 2-volt wire and my negative lead is connected to a 1-volt wire, what does the voltmeter read? 1 volt. If my voltmeter is connected to a 2-volt wire, positive, negative is connected to a 0-volt wire, the voltmeter reads 2 volts. And then on this one, showing a 12 and 5, again, difference in potential. A voltmeter reads the difference in potential. Okay? And then one other aspect of this, I skipped it, because we already talked about that, is voltmeter provides an average reading, figure 13. So what I'm showing, and we'll go into more of this, I have some videos on this too, on the average reading voltmeter, Chrysler Hall effect crank sensor. Check out that video, and I'm showing these kind of signals with a voltmeter. Notice in the top picture, what do we see? We see a 0 to 5 volt square wave. And in the bottom picture, what do we see? We see scales are over here. What am I looking at? Okay, couldn't see the decimal. 0 to 5 volt square wave. What do you think the average is of a 0 to 5 volt square wave? You would think, if you just spit it out quickly, that it'd be 2.5 volts. But it's not. Because the average has to do with the characteristics of the waveform. Average is going to be the high time compared to the low time. So the top picture, is it safe to say that the top picture, the low portion of the signal, is pretty close in time to what the high portion of the signal is going to be? Would it be safe to say that? That it's pretty much low about the same amount of time as it is high. So what's the average of the top signal going to be? It's 2.5 volts. I'm showing you that right here. The average of this waveform is about 2.5 volts. Okay? In the bottom picture, would it be safe to say that the low time is equivalent to the high time? Not a chance, right? Isn't it low a lot longer of a period of time than it is high? So wouldn't it make sense that my average is going to be much closer to the ground side, the low side, than it is to the hot side, which would explain that number. All right, now what's the point of this? If you're checking a crank sensor with a voltmeter that has a square wave, you're not going to see the square wave. You're not going to see this. What are you going to see on your voltmeter? That. And it's going to be steady while you're cranking. You don't even know there's an on-off signal taking place, but there is. And your voltmeter's averaging it. So another characteristic of the voltmeter, it averages signals. All right, we're going to take a break, and then we're going to cover these two. We've already covered the limitations of this ohmmeter, but there's a couple other things I want to share with you with that.